would we be without GNSS or GPS? Completely and utterly lost. Well, I would be for absolute certain. I'm one of those people that turns the wrong way always. So if you see me walking one way, most likely you'll want to go the other way. But how has GNSS and GPS evolved over the years? And what kind of improvements are we seeing these days? Well, let's talk about it. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Pat Frank from Taoglas and I explore the details of multi-constellations GNSS systems. We also investigate the key characteristics of antennas and how you can future-proof your GNSS design with Taoglas's antenna solutions. And before we get started, don't forget to click that link. There you can find even more information about this topic from Taoglas. Hi, Patrick. Thank you so much for joining me.
Thank you.
So, we're talking about the evolution of GNSS today, but let's start at the top. Patrick, what kind of benefits does multi band GNSS bring to the table?
Right. Yeah. So there's really like a couple main benefits that come when we're talking about multi-band GNSS. And really, it's accuracy and reliability. And as you go through a number of different applications, you can weigh the differences between, is this important for me or not? So if we look at certain applications like an autonomous vehicle or automated driving car, it's pretty clear that we want not only accurate position, but reliable position. And as we go through different applications, maybe wearables, we really appreciate having a more accurate position. And as we go to other applications, you go to something like an asset tracker, then really maybe you don't need the same kind of highly accurate or highly reliable position. There's another benefit that comes with multi-band GNSS, and that's more accurate and more reliable timing. And this is maybe something that kind of hides in the background in a lot of applications. I think a good example for me is for 5G. So if we go to look at 5G, one of the features that was brought into 5G was this kind of close coordination between base stations. But one of the enabling technologies that's required for that is to have really accurate, really precise timing. But not only that, 5G, we really depend on our cellular networks quite a bit. So having reliable timing also is really, really important. So I look at it as accuracy and reliability.
So, Patrick, walk me through the details here. This ensures that redundancy is built in, correct?
Right. Yeah, exactly. So this is kind of tangential to multi-band. And there was a time when we talked about bands in terms of constellations, and that's kind of just got things a little bit confused. But here, really what we're talking about, this is a secondary thing. So constellations is GPS, Galileo, GLONASS, and BETO. So having four different whole sets of satellites in the sky that are available for us to use for our location. And what does that do for us? Well, that gets us all the benefits of having so many different satellites in the sky. So reduced signal acquisition time. It gives us improvement because of just having that in the many numbers. So we get, reduction of problems caused by obstructions. So if the three GPS satellites are being obstructed, maybe you have four Galileo over in another part of the sky that you can use. And then just having more satellites spread across the sky gives you better geometry, which we call dilution of precision. So just better geometry for things. And then all that adds up to improved position and time accuracy, in addition to having some redundancy. So if the GPS system is down, for example, there's three other constellations available for that position and time.
So, can you give me an example of this kind of system?
Sure. Yeah. The GPS is a great example. We'll walk through how this works and what this looks like. So when we look at GPS satellites have been up for quite a while, and all of the satellites to date have had one frequency band, that's L1, 1575.42 megahertz. All of them have that. And that's kind of the classic GPS frequency. If somebody says GPS and you think of a frequency, this is really the one, 1575. So it's a legacy, and it's on all. It's not going anywhere. It's going to stick around for a while. It has civilian signals. There's also a couple of other signals available to it. And then, really, when we look at the technologies, we look at the receivers available and what kind of accuracy, kind of focusing on that part of it. About the best we can do is we call it a 3-meter accuracy. And that's taking everything that we know for a standalone GPS receiver gets us about 3 meters of accuracy. All right, how do we get better accuracy than that? Because I think for some applications, going back to that autonomous vehicle, like that's too big of a range. Like that's being in one lane or another lane. So we really need something better than that. So how do we do that? Well, it turns out that actually a big part of a lot of that air that comes in is from actually a part of the atmosphere called the ionosphere. And really, there's maybe a couple of ways of dealing with that, but one of the best and most reliable ways of dealing with that error is by adding a second frequency. And that's where we get this multi-band concept. And that first second frequency was L2, 1227 megahertz. And this has been on all GPS satellites that are in use right now have L2 available. And the use of these two signals allows us to almost cancel out that error that was introduced in the ionosphere. And that gets our accuracy down to that 1.5 meters. So that's much better. Now we're talking about a single lane of driving rather than am I in this lane or that lane. Now, as part of modernizing GPS, new satellites that are being put into orbit have an additional third frequency, and that's L5. That's pretty close to L2, and it's 1176 megahertz. So this is again available at all newer satellites. And really, what it was intended for was it was looked at and they said, okay, we have some pretty important applications. Aviation is actually what they had in mind. And let's make sure that we can have a signal that's as reliable, stable, and provides the most resilient position possible. So that's where L5 comes in. It has advantages over L2. It has more power and it has a higher gain. So there's just more available from L5 than there is from L2. However, in both cases, L5 or L2, you still need to use them together with L1 to get that improved performance. Now, you can use all three together. Some receivers do that. And then you can, kind of going back to that last topic, you can add in additional constellations, and that can further improve the picture. Now, that's 1.5 meters. How do you get even better? That's where these other two frequencies come into play. The first one, both of these, when we were talking about further improving accuracy, really what we have to do is we have to supplement the signals that are coming from those satellites like GPS with additional things. We call them correction services. And that can come from a few different places. One can be from this L band. So this is a signal that comes from satellites. Also, it comes from different satellites than GPS or Galileo or GLONASS or Beidou. They provide different data that help us correct the signal even more. And that can get us into the decimeter range. And there's a similar kind of signal that will be available at E6. This is from Galileo only. It's called a high accuracy service and will provide, again, not locating data, but corrections data. Now, there's an ultimate kind of corrections available, and that's called RTK, or real-time kinematic. And with that you can get down to a centimeter level kind of positioning.
Wow. Okay. So, Patrick, what impact did these other bands have on antenna and RF solutions?
Right. Yeah, exactly. There's no such thing as a free lunch, is there? And so the left antenna that we're looking at is our CGGBP.25.4. That's a 25 millimeter square, 4 millimeters thick. That's kind of your classic patch antenna that we think about and you associate with GPS. And that's single band. The quad constellation supports GPS, Galileo, GLONASS, and Beto, but it's single band. It's L1 only. Now, let's say we want to use L2 and L5. That gets us to the antenna over there on the right. That's our GPDF 5012.A. That's a L1, L2, L5, supports all four constellations. But now we look at the size. That's a 50 by 50 by 12 millimeters. Quite a big difference. And then looking at complexity, we can see that increase in complexity also. Looking at a similar kind of antenna, we can see that with that antenna, there's more pins. There's things we have to add. We have to add hybrid couplers. We have to have amplifiers, filters, and now that's at two different bands. So here we show our HP24510A, which is a L1, L2, I believe. And we have two hybrid couplers, our TFM.100A front end electronics module. Many different things are pulling together here to enable that higher precision. So many different parts.
So, the idea of future proofing is crucial here, right? So, how do you guys help with this issue?
Right. Yeah, exactly. So having, a solution and implementation, a positioning solution that really works for yourself for the long term. If you stick with a single band, is that really going to provide the user satisfaction? Is that going to enable the future solutions that you have in mind for your application? Or are you going to need something more? And if you look down the road, do you need something more? That very well might look like adding multi-band GNSS receiver and all the things that go with it. So typical for that single band design, again, that 25 by 25 by 4 patch antenna. Maybe you have similar kind of thing with an active antenna that's off board, but that's really locked you into that single band topology. Now, if you think you might want improved positioning, more resilient timing, that can get you cleaner signal, better accuracy. So looking at what are my options now? And do I want dual band, triple band, all the bands? Well, that's just it. So prices are coming down, the technology for a lot of these things, especially the receivers compared to 10, 15 years ago. The receivers are in a totally different spot. And looking at our antenna solutions, we have solutions that are single band. We have antennas that are dual band, triple band, support all the bands. So whatever you need in many different size factors. So we have solutions that work for whatever your device, whatever your application. We probably have something that slots in, can work, and help to provide a future proof solution for you. Because all these new bands aren't going away anytime soon.
So, what kind of antennas does Taoglas offer?
So, as mentioned, we have a wide range of antennas available for single band or multi band GNSS. And really, what we're trying to do is we're trying to make sure that customers of ours in many different applications can find a product of ours, find an antenna that meets with their requirements for position, robustness, and performance in the package that they're looking for. So we have everything at the very low end of the scale. The chip antennas, we have the GGBLA.125A. It's linear polarized antenna, but it's very small, it's very high efficiency, it's very good for very compact installations, very compact applications that are maybe mobile, but you want to get the benefit of, for example, using L1 and L5. You can get a lot of that benefit with a very simple chip antenna. Moving up, we have flexible PCB antennas. Again, linearly polarized. We have a few different sizes, passive and active. And again, this works for a lot of applications. You want to peel and stick inside of a larger housing. Or we have the classic patch antennas. We have dozens of different patch antenna sizes that support different bands, slightly different form factors, different ways of applying it, passive and active. And really, this is the classic that most people will land on for an embedded solution. But we have whatever the band configuration that you need, we have an option for it. Moving up into larger, maybe you need something that's more robust that might go into an external or some piece of machinery or some sort of autonomous vehicle. We have a few different external options, and here's a couple. We have a cross dipole option, the XAHP50, that features very low cross polarization, very good antenna performance, and a pretty compact package. And then going up, we have quad helical antennas that have excellent circular polarization, purity, excellent performance, omnidirectional, again, passive or active. So, whatever it is, the application, we strive to be able to scale to the size, cost, and performance that you need.
So, Patrick, what are the key characteristics of antennas that we should keep in mind?
Right. Yeah, exactly. So, traditionally, with GNSS single band as solutions, you'd really focus on antenna gain and maybe axle ratio, maybe. Now we're going to higher precision and multi-band. You're really kind of taking a closer look at maybe how do I get better performance out of my device. Then you have to look at a few different variables, a few more different characteristics. So antenna gain is probably still the maybe the most important characteristic that you have to keep an eye on. Gain or efficiency, depending on if you have very mobile application, then maybe you'll want to look at the efficiency more. But most applications you want to look at antenna gain. That's in dBi or dBIC. Secondly is axial ratio. So this is a description of how pure is the circular polarization of this. So the signals that are coming from the satellites are circularly polarized, and ideally the antenna is receiving in that same way. So the axial ratio is a measurement of that, and 0 dB is a perfectly circularly polarized antenna. And linear antennas doesn't even matter. You just don't even look at it. But for a lot of antennas, especially if you're really trying to get to that decimeter or trying to use RTK, that axial ratio can really start to have an impact. And that can also kind of have a knock on secondary effects where having a good, clean pattern will start to have effects on these other characteristics. So, phase center offset. Hear this a lot. You see this a lot on high precision antenna data sheets. And what does it really mean? Well, the phase center is where the GNSS receiver actually calculates its position. So when it gets a position, a three-dimensional coordinate, that's actually the position of the where it thinks it is, where the phase center of the antenna, or PCO. And now no antenna is perfect, so that phase center offset might be off a little bit from the geometric center of the antenna. So PCO. How does that change? That might actually change as you look at it over the course of the sky. So as a satellite moves across the sky, that might actually impact where the receiver actually calculates its position. That's the phase center variation. Lastly is something called group delay variation, sometimes called GDV. And this is how the antenna, how the filters distort the signal, GNSS signals, in time. And that can cause a distortion in the position. So all these factors together really come to bring together the ultimate accuracy. And often we'll use this 2D RMS term, which is where if you have all the points, the calculation over a certain period of time, you draw a circle around 95% of them, and that's your actual accuracy.
So, there are passive and active antennas as well, right?
Right. Yeah, exactly. This can cause some confusion because we have both available, and we'll get this question a lot. Which one should I use? Should I use a passive antenna or should I use an active antenna? And I look at it. So if you look at your receiver, so you look at that first, and if your receiver already has an LNA or low noise amplifier inside, and your antenna is pretty close, maybe it's on the same board, you just have a trace connecting the two, then you're probably okay to just use a passive antenna. And then you avoid a lot of the complexity that comes with having an active antenna. And that will be true for single band or multi-band. Now, if your receiver does not have an LNA or low noise amplifier inside, then you definitely need an active antenna. There's no question about it, no matter how close or far away your antenna is. Or regardless of whether there's an LNA inside the receiver or not, then if your antenna is pretty far away from your receiver, then you really want an active antenna also, just to avoid any additional losses or distortions or things like this that can come from having a long cable, for example.
Excellent. Well, Patrick, I think that's all I have time for today. Thank you so much for joining me.
Thank you so much for having me.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Taoglas. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.